beautiful time to actually mention or introduce frequency and wavelength, okay?
Properties of a wave.
So
it's a good time.
as the object is vibrating back and forth, the amount of times that it vibrates back and forth in 1 second is the frequency, and that actually comes in units of hertz, 1/seconds. Okay, so everybody's heard of hertz before, this note is 20,000 hertz or whatever.
Oh, that's high.
That's very high.
That's literally the limit of human hearing.
That is the limit.
Relax. Yeah,
but now you know what that means. When you hear something that has a certain amount of hertz, it's because it's literally moving back and forth, and it's causing your eardrum to move at that same frequency at 20,000 times per second. Okay. Now imagine this. Okay, I make a noise, and it produces these high and low pressure columns that are moving at the speed of sound, which is 344. I thought it was 344.
Something like that.
Whatever.
Like that.
The thing about sound is that the speed of sound actually changes based on the medium. Okay, so it's different in water or metal. It still works in metal, but we're not going to get into that right now. What I'm trying to say is that the speed of sound in air is relatively constant. Let's say, it changes with temperature, right?
Of course.
Yeah. Anyways, we're gonna pretend like it's constant for now because we're in ideal conditions. And now let's say I produce a noise, and we take a snapshot in time of the high and low pressure columns. Okay, based on the frequency, you can deduce like how many of those columns would be in between Ray and I. Now, what would happen if Rayhan's ear is moving towards the noise that I'm making? Well, his eardrum would literally be experiencing those columns faster than they were moving towards him if he were to be still, right? Like imagine there's a bunch of waves on the ocean. You could either be standing still in the waves, or if you're on a jet ski, you're going to be experiencing those waves at a faster rate. Now, what does that translate to when we talk about sound? Well, I just mentioned 2 seconds ago that the rate at which something is vibrating is the frequency, right? And lower frequency is lower pitch noises, and higher frequency, higher pitch noises. Okay. Now I am producing a noise. Rayhan's eardrum is coming towards that noise, and so it's the jet ski going through the waves, experiencing them faster. All of a sudden, his ear is experiencing a faster frequency than what was originally exiting my mouth. Now, what does he hear? He hears a higher pitch noise. Now, think about this. When you're on the side of the road and an ambulance is coming your way, that ambulance is the speed of the ambulance is adding to the speed of the sound that is coming your way. So the waves are getting pushed closer together, and when they hit your ear, they sound like they're going faster than they actually are. Now, when the ambulance passes by, it is moving away from you. The source, or I guess it's all relative. It is a source, but it doesn't matter. The ambulance could be standing still, and I could be going the other way.
Yes, of course.
It doesn't matter.
If the ambulance is moving away from you, or you are moving away from it, is what
the only thing that matters is that there's separation happening. Right now, all of a sudden, I'm going the other way, and now my ear is hearing the noise, but at a slower pace, and what you hear is right. It goes high and then low. That's what you're hearing.
Yeah, and that is the Doppler effect.
That is the Doppler effect.
That is the Doppler effect. So probably by a guy named, it is obviously.
No, 100%.
I just forgot the guy's first name, but obviously crazy. But what it actually shows is that nothing fundamental is actually changing about the wave, except for the one fact, or except basically for frequency. So the speed is staying the same, which is interesting, which is a very nice thing that you brought up, but the frequency is changing. Also tells us something about the relationship between the frequency and the speed. Like how is somehow the frequency or the pitch getting louder, but the speed somehow not increasing or decreasing? Well, that's simply the equation of speed, right? That's simply how frequency, speed, and a property of wavelength are all related to each other. And it's quite intuitive to see that if you were to increase the frequency, as in, I'm just thinking of someone who hasn't heard of frequency before. Like if you draw one whole wave in a certain interval, now draw 3. That's increasing the frequency. It's just intuitive that the spaces between the waves get smaller too. It's just intuitive, right? You can almost see it in your head. So when one goes up, the other comes down to keep that constant.
Yeah. And also, quick fun fact, when you see like an airplane going faster than the speed of sound and you have the sonic boom, that's literally because the airplane is creating a noise, a loud noise. It's vibrating the air around it, and it's creating these high and low pressure columns everywhere around it. But what happens is that the faster the airplane travels, the closer together he's squishing those columns, right? As we just talked about the Doppler effect. But what happens when the columns get squished so close together that it's infinite, that it's pretty much like it reverses, you know what I mean? Like the noise gets produced after the event happens. There is a barrier there, right? Of course, because you go from sending waves forward to compressing them and then sending waves backwards. And that is where the boom happens, because you have to literally squish those high and low pressure waves to essentially zero.